Just hello, hello. Hi, everyone. Let's get started with today's lecture. So we're doing integration by substitution. So we're just, keep stacking on, the difficulties of integration. The idea from here is that integration, using some previous, just copying and pasting the idea of a derivative and an antiderivative. That's what we've been doing. And at the moment, that's very palatable, right? We're literally just going backwards. However, obviously, not all functions are generated equally, right? So, let me read this prompt first in case I'm skipping anything. The fundamental theorem of calculus gave us a method of evaluating integrals without using the Riemann sums. The drawback of this method is that we must find the antiderivative, which is not always easy. Okay, it's kind of what I'm talking about. The method of U substitution helps us find antiderivatives when the integrand is the result of a chain rule derivative. Recall the chain rule. When you take a function of within a function's derivative, right? All of which is respect to x, you have a product. You have the derivative of that function with the original intact, and it's multiplying, emphasis on multiplying, the inside's derivative. Now, let's start off with over here. So over here, we have a function within a function. Clearly, this guy over here is a function, let's label it f of, let's say, u, and we'll say it's 2 over 3 u to the power of 3 over 2. And then the inside u is 4x squared plus 1. Well, we know that what we do is we first do derivative of this guy, which you bring the power here, so 2 over 3 times 3 over 2, and then subtract 1 from here, so you get u to the power of 1/2. This just simplifies to the square root of u, and then over here, you need the derivative of u, so that's going to be 8x. So, going back here, you'll get the square root of 4x squared plus 1, then times u prime, which is just times 8x. Now look over here. You can guess then that this will be the answer. But let's just pretend, just for the moment, that you don't have that comparison. How would you do this? Well, you see that these are two functions multiplying. So you have that bit of a hint that there's a chain rule U substitution idea. Now, what you want to do, there's several strategies to do these. I argue that you want to make the answer as easy as possible, the integral as easy as possible for you to do. So you could say that wouldn't it be easier if this was all one variable? So you go u and you say it's inside that whole variable, 4x squared plus 1. However, if we're doing this integral with respect to u, then we need to account for doing the integral with respect. We're replacing part of the integral to be of u, then that means we need to replace this part as well to be of u as well. So we need to do that derivative. So u prime, or I'll just say du for this notation, will be 8x, and then times dx. Now, note here that you are presented with an 8x and a dx. So, you take what you need to replace it with du and replace what you need for u. So, we see here, I'm going to do some highlighting for this actually. So, we see this 8x and this dx all become the du. And then that whole expression here becomes that u, so square root of u. So we know the integral of this is simply just, if you rewrite as a power, you would do u to the power of 1/2 plus 1, which is 3 over 2, and then divided by 1/2 plus 1, which is 3 over 2. To make it a little bit easier for yourself, we're going to go ahead and just put that on top. So 2 over 3 times u to the power of 3 over 2. And then we plug in back what we originally had for u, which is, oh, and I forgot plus c, excuse me, plus c. 4x squared plus 1, and then to the power of 3 over 2 plus c. So kind of like the examples we did before, we can see that it's just a copy and paste. I'm sorry, it's just a copy and paste, but with the plus c. Now, there's multiple ways to think of these strategies. I like the method personally. I learned the method of, well, let's make it easier. Another method that you could also see it as is, well, there has to be a derivative within here that you see. So I'm actually going to skip example 3 just to prove my point a little bit. Or not skip it, I'll do it right now, but I just want to prove my point. So you should see here that there is a derivative and its function multiplying each other. So what you can see, actually, is this. x3, its derivative is 3x squared. So you know that, okay, well, there's some substitution that you can do here. Now, granted, if I do u is equal to x3, and du is equal to 3x squared dx, keeping the notation of the dx alive, you can see that the substitution, let me use an erasable pen for this, would be u plus 1 to the power of 4 times du, which honestly makes the problem a bit more annoying, and you would probably have to do another set of substitution. So you might as well, in cases where you can see it being snuck in, include any constant. Because you know the derivative of any constant will just disappear. So in that way, you can redo it as a simple integral being u to the 4th du. Now, the notation of du and dx, that's, I think I glossed that part when I said it over here. That's going to be from the fact that when we write derivatives, right, we do, I'm going to actually write it here. We do u prime, we write it as 3x squared, like what we see normally. But instead of this notation, you do the other notation, du over dx. And then, treating it like a fraction, multiply both sides with by dx, and you'll get this guy over here. So you can treat it like that. In fact, I'm going to probably copy that for this question, but let's just do these two to see if our work is valid. So you're going to get u to the power of 5 over 5 plus c, and then you plug in u. You get parentheses x cubed plus 1 to the power of 5 over 5 plus c as your answer. Now, this is also a good idea to mention that whenever you do the derivative of the answer from the integral, you should get back whatever's in the integral. So let's see if we can do that here. So I'm doing the derivative. I know I can take out the constant first, and I'm left with the derivative of this full expression. So that's just a chain rule. You do the 5 times x to the power of 3 plus 1 to the power of 4, and then the derivative of what's inside, so 3x squared. And it looks basically the same. The only thing that we need to do is simplify that to just disappear, and we're left with the answer. So you could think of it as the shorthand. Okay, what substitution would make my life easier? You could think of it as the other shorthand of, okay, so from here, there's a derivative of one of these multiplying, emphasis on multiplying functions that's within this integral. Where is it? Or is it even there? Okay. So again, you see here that you'll have u be 4x. Why 4x? Because its derivative 4 is present. And then to copy the notation of the integral, you do write it like with this notation, and then multiply everything by dx. And you see that this substitution holds. We do 4x here, and this one, although it's not directly stated, you take the 4 and you take the dx. So you're left with the integral of sine of u du. That's just negative cosine of u. And then you're going to go ahead and, oh, sorry, plus c. Then you're going to go ahead and plug in u, which is just negative cosine of 4x plus c. Let's check that derivative here. We definitely can take out the negative derivative of cosine of 4x. That's just a chain rule. You're doing a negative sign of 4x and then times 4, which that'll be positive, and then you can just write the foreign sign of 4x. Okay? Alright, so the thing I will say, and the reason why I kind of don't like this method, and I believe we're going to experience it in the next problem. If not, I'll make one up right now. Yes. So sometimes you don't see a complete derivative with multiplying each other, but you see pieces of it. So what do I mean? Let's go here. Again, if our lives would be easier if all this was one variable. So u is 4x squared plus 3. And we know the derivative of u is simply 8x. And then with the dx. The problem here is that we do not see ax, but we see a piece of it. We see x. And with any equation, we can simplify it a little bit. We can divide both sides by 8, and then rewrite it just a little bit as 8 times du is equal to x dx. In that way, you can make the substitution, just like how we had it before. This whole piece will take up the u, and only this whole piece, which is right here and right here, will take up the du. But du has an added bonus, 1 over 8. So I'm going to go ahead and write it with that substitution in mind. 1 over 8, 1 over u squared, and then du. We know the property of integrals. We can let the 1 over 8 escape. 1 over u squared du. We know that's just negative 2, so we can rewrite that as u to the power of negative 1 over negative 1, and then plus c, and then simplify what we can. So I'm going to go and get a negative here, 1 over 8, 1 over u, plus c. And then we're not done because we need to plug back in u, which is 1 over 4x squared plus 3, and then plus c. This matches that, with the exception of the c disappearing, right? But we can safely say that this will match. We have negative 1 over 8, and then the derivative of 1 over 4x squared plus 3. So we do that derivative first. That's again, obviously via the point of this lesson, another chain rule incident. You'll do times a -1 and then 1 over this whole thing squared. And then the derivative of what's inside, so times 8x. So we have a couple of things. The 1 over 8 and the 8 will cancel out, and the negatives will cancel out. So you're left with x over 4x squared plus 3, all of which is squared. And that would be your answer. Now, granted, and just to bring it up again, that's why I encourage both, I guess, lessons. You want to ask, okay, well, what derivative is multiplying here, right? Is there a derivative of this hidden somewhere here? And there technically was, right? The other, I've seen it done this way, and I kind of don't like it. Here, actually, let me just show it to you guys. What you could have done, right, is in order to make the derivative appear, you factor out this. So, for example, or you just rewrite the rules a little bit. So if you saw 4x squared plus 3, and you're like, well, if I multiply by 8, it'd be there, which you can. You can multiply by 1, but instead of writing by 1, you're going to write 8 over 8. You'll get this integral, if you multiply by that 1, you'll get 1 over 8, and then 8x over 4x squared plus 3 squared, and then dx. And then you could do the substitution plainly. Now, it's not that I don't like that, it's actually pretty fine. I just don't know what you guys would prefer. Because that's one of the difficulties is being online, right? There's a lot of ways to tackle these because at the end of the day, I'm asking you to tackle essentially trick questions, but the tricks are not, you know, crazy. They're not like unknown. So you have to do some workarounds. Here, you kind of just make it disappear by adding a multiplicative constant. Okay? Here, we're going to see that it's also not that easy. But it's still very doable. So, for example, you have u again, and you're asking yourself, well, what's easier? Well, I don't know about taking the integral of sine to 4, but if it was like a regular variable, I know I could. And I know that the derivative of sine is cosine, and that appears here. So I take u with sine of x. Oh, it appears here via multiplication. If it was add cosine, that ruins everything. But if it's appearing here via multiplication, then we can do it. Du is equal cosine of x dx. So you have that filled in here. And then you have that filled in here and here. So you have u to the power of 4 du, which we know is u to the power of 5 over 5 plus c. And then you plug in u. So sine of x to the power of 5, you can write it here, over 5 plus c. And then we see that that's basically what's going to happen. 1 over 5 times 5 sine of 4x, and then multiply its derivative times cosine of x. And then that will just cancel out, and you're left with sine to the power of 4x times cosine of x. So again, we're repeating the sort of idea that these guys are opposites of each other. If you do derivative of a function and you get out this, then doing the integral of that same function should give you back what the initial derivative you took out, with the exception of that plus c that has appeared everywhere. Let's do this one now. So this one's a bit tricky. For one, it's a definite integral, so it has bounds. But you still need to do the indefinite part of it, the antiderivative classic part of it to solve. So we look here, and we again have a technical issue where we see that if I do use this, its derivative, which is just 4x dx, is not exactly there with the exception of before. So you have multiple choices to do this. You can either rewrite this rule, you can multiply the 4, but then later divide out the 4, hence that multiplying by 1 trick. Um, I'm gonna show you the other step, but I actually really don't like it. I think it's kind of ugly looking, if I'm honest. What you do is you let the 2 escape. So, I'm gonna show you it, but I hate it. I'm gonna be so honest. I hate it, but I'd rather just show it to you for funsies. You let the 2 escape, so it's x squared minus 3 over 2 to the power of 5. And then because it's a power and these two things are multiplying, you get split up that way. X times 2 to the power of 5 times x squared minus 3 over 2 to the power of 5. And then from here, or actually, oh, it's a whole another thing. You would have to take out enough so it's 1 over 2. Okay, I'll do it, but I'm gonna, that's why I'm writing in the eraser pen. I'm gonna erase this all. You can copy this down on like a separate sheet of paper if you want, but this is not gonna make the final draft because I don't even like this method. The goal is that you take out enough so that way when you do get the answer, when you do the derivative, you can see that that guy's derivative is right there. Very little substitution required. And you also let the constant sneak in as well. Um, I guess let me keep going. I don't like it, but I'm gonna keep going just because I'm trying to prove a point. Minus 3 over 4, that derivative is just gonna be um x dx. Oh, I forgot the dx here as well. So we know that will become 4 to the power of 5, and then that's gonna become u to the power of 5 du, which can be rewritten as 4 to the power of 5, 1 over, or not 1 over 5, u to the power of 6 over 6, and then plus c. And then from here, you can go ahead and then do this power problem from 0 to -1. I really don't like this. This feels already too messy. Oh, I forgot plug in x back. Excuse me. So I need to plug in x back. So it's gonna be 4 to the power of 5. But at this point, I'm already gonna get rid of the c. You have parentheses x squared over 2 minus 3 over 4 to the power of 6, and then over 6 for 0 to 1, -1. Ugh, I hate the way this looks, but I'm gonna keep going. When this is 0, the whole thing will be 0, and then you're left with 4 over 5. Or actually, let me take out the whole thing. When it's 0, this thing will be -3 over 4 to the power of 6. And when this thing is -1 minus, let's just simplify 1 over 2 minus 3 over 4 to the power of 6. Ugh. Okay, 4 over 5, 6. That's gonna be it's gonna be a very ugly number. That's technically doable. Here, I'm actually just gonna keep it as a fraction, but still perform it. We have 3 to the power of 6. So 729 over 4 to the power of 6, 4,096. And then that's going to be it's minus, and then that's going to be negative 1 over 4. So negative will cancel out, and negative 1 over 4096. Okay. Um, or actually, I should have kept it as 4 to 6. Let me do that. 4, 6, 4, 6, because technically you'll get 4 over 5 over 6, and then times 2, 7 to 8, because the minus 1, over 4, 6. That will cancel out. 7 to 8 over 6. That, I think it's not divisible by 6, or let me check. It's not divisible by 6, but it's divisible by 3? No. It's by 2. So let's do 2. So we get 364 over 3. Let me see. So funny enough, that doesn't match my answer, but I do want to double check. So making it 0. We've got that over here. Then the negative becomes positive, 1 over 2 minus 3 over 4. I took out the dividing by 6. What am I missing? Let me see. Um, let's see. Did I do the power rule wrong? I don't think so. Let's just leave it as is, I guess. Ah, dang it, because my answer here says 91 over 3. And that's what doing it the prettier way. Um, I guess let's try to just keep it the prettier way on the side, and I'll leave the ugly way here for a little bit longer. So recall that du is not present, so we have to divide both guys by 4. And then just for technical purposes, I'm going to rewrite as 1 over 4. Du is equal to x dx. So you plug that in, you get control of u to the power of 5, 1 over 4 du, from 0 to negative 1. 1 over 4 for u6 over 6, 0 to negative 1. And then you get, let's simplify this a little bit. 1 over 24 u6 from 0 to 1, negative 1, and then I'm going to plug in u. Two x squared minus 3 to the power of 6 from 0 to negative 1. 1 over 24, for when this is 0, you'll get negative 3 to the power of 6. And then, when you get negative 1, you'll get this value to be negative 1 as well. Yeah, 2 squared, that's 1. And then 2 minus 3, yeah, so you'll get minus a negative 1 to the power of 6, which is just 1. And then, yeah, you get 270. Oh, I cancel them all out, but there's a 4 hidden here. That's why. Okay, cool. So let's go ahead and divide out, well, That's the same, 364 over 3 times 4, and then now divide that by 4. So 364 divided by 4, you get 91 over 3. So 91 over 3 is your answer, and that's what I had in my work. So just to come back here, this is very ugly. We agreed this is ugly. However, the only reason why I'm including this, even temporarily, is because technically speaking, one could argue that this is what's going to organically happen for you guys. Organically, you're going to see it as well, if the pattern is that its derivative has to appear as a product or as a multiplying term, you can manipulate however you like so it does appear. The manipulation here, though, is a bit easier, right? Because you're just multiplying something by 1. However, the manipulation here, which is a very overly dense factoring, is a bit more annoying. So I leave it though to you guys technically on how you want to do it. So 1 over 24, that's gonna be 729 minus 1, and that's gonna be 728 over 24, and then because we know that was divisible by, I think they're divisible by 8 because we divide a 2 and a 4. So we divide both guys by 8. Or we just keep actually, let's just do organically. Let's keep dividing by 2. So 278 divided by 2, 364 over 12. And then divided by 2 again, 182 divided by 6. And divided by 2 one last time. 91 over 3. And that's your answer. And that's what we got. So, just keep that in mind. This whole idea of a chain rule. Your homework that you're gonna get today and the worksheet that we're gonna do today, it's gonna test you, but it shouldn't make sure that you really encapsulate like all of what you're doing. Because this is the part where I worry the most because the strategy, I can give you every other strategy in the book and we could Google and figure out other strategies. But the strategy you end up picking is going to be up to you. It's not necessarily my place to tell you what strategy is what. I can just give you my opinions. So you have several strategies. You have what makes your problem easier. You say that with air quotes. What term appears as a product of its derivative? So that term divide or multiplying it, you see that its derivative is there as well. Or just okay, what can I manipulate so that way one it's easier or two its product appears as a derivative. All right, so that's gonna wrap up this part, guys. Let me know if you have any other questions, and I'm gonna see you in the next video. Bye bye.